Okay, hello. I changed my title a little bit. That's not significant. I just thought it was a little bit too long. So we're going to be focusing on the continental lithosphere, actually, because of its relevance to the topic of this summer program. So first, I wanted to go over the seismological tools that we have to investigate the upper mantle, the lithosphere, asthenosphere structure. I'm not going to be talking about the crust. I'm mostly going to be talking about deeper structure. So we've already seen that seismic tomography, surface waves, and overtones of surface waves are essential to study the upper mantle because they provide the resolution, both lateral and depth resolution that you need at these depths. However, they provide information on volumetric distribution of heterogeneity and the relatively large scale, smooth type of heterogeneity. The depth resolution is good, but it's not necessarily what we need. It's on the order of 50 kilometers, roughly. I already mentioned in my previous lecture that overtones are important even for the study of continental lithosphere because the fundamental mode starts losing resolution around 200 to 300 kilometers. And as I will be discussing, there are additional constraints, important constraints, that we can get from seismic anisotropy. I'll be talking about this later. Another type of observable or seismological tool is the receiver functions. They are sort of complementary. They don't give you the large-scale structure, but they allow you to detect sharp boundaries within structures, such as the MOHO, the lithosphere-asthenosphere boundary, which I'm going to denote as LAB, and maybe some mid-lithospheric discontinuities. There are additional types of data, for example, long-range seismic profiles. These are profiles that are several thousand kilometers long. Most of them have been done in the 1960s, and a lot of them in the Soviet Union. They require doing, you can't use, well, most of the time you use artificial sources, so they need to be rather strong, and in particular in the Soviet Union, they had this so-called peaceful nuclear tests that were very nice for this purpose, but there have been also long-range seismic profiles in Europe and in North America. These also can be used to map sharp boundaries and regions of strong scattering in the lithosphere. And then I'll be discussing also shear wave splitting analysis, which ties into the study of anisotropy in the upper mantle. I point out here that teleseismic P and S wave travel times also provide constraints, but they only provide constraints really on the average velocity across the upper mantle, because as I explained last time, they do not provide the resolution. You don't generally have crossing paths that would allow you to have the depth resolution you need. I mean, there are smaller scale studies that can, but in general, the main constraint is really on the average velocity at a given point. And the focus is going to be on Archean Cratons. So Archean Cratons are the stable regions of continents which have been relatively undeformed since the Precambrian times. And we can ask a number of questions and see if seismology can help us with this. You know, what is the structure and how did they form? How did they form? How come they remain stable since the Archean time? Fundamental question I will be spending some time on is how thick is the cratonic lithosphere? And then can we put constraints on a thermal structure and composition? So the way we think about the continental lithosphere is as the layer that corresponds to the conductive geotherm, and essentially the one definition of the lithosphere is the intersection between this continental geotherm and the convective adiabat which happens at some depths, which from various types of geophysical data turns out to be around 200 kilometers, for example, heat flow here. And you can also think of it as I will develop, more as consisting of some parts that may be chemically distinct from the rest of the upper mantle. And there's also an aspect in terms of strength, that the lithosphere, continental lithosphere, is stronger than the underlying mantle. Yes?
So when you say the lithosphere is defined by the crossing of these two thermal profiles, I thought it's, you know the boundary first, then you establish the geotherm, right?
No, the geotherm you define from heat flow measurements and composite, sort of conductivity. So you do define this slope here, this by other independent measurements. So Tom Jordan introduced in the 1970s this idea of Isopycnic hypothesis. There is, whereas as we will see, seismic velocities are fast in the cratons. We know they are cold from geochemistry and heat flow measurements, but there is no signature in the geoid, for example. And so somehow they have to be compensated. And this isopycnic hypothesis says that the temperature difference between the cratonic tectosphere and the convective mantle is density compensated by the depletion of the tectosphere in iron and aluminium relative to magnesium by the extraction of mafic fluids. So it's this concept that the continents are floating because they are lighter, right, than the surrounding regions. Whoops, and this is Tom Jordan's cartoon here. So one important question which is still being debated is how thick is the cratonic lithosphere? So yes, you can define it from the geotherms, but how do you define it from other types of data? And so Tom Jordan's tectosphere, which may or may not be equivalent, the same thing as the lithosphere, was initially defined as something that from seismic data as reaching down to 400 kilometers. On the other hand, as I mentioned, heat flow data and other types of geophysical data such as magnetotelluric and xenoliths indicate more something around 200 kilometers. So there is already a question here of, what are we looking at? Are we looking at the same thing, and how can we reconcile it? And recently, as I will show, receiver function studies have this particular one, but not only this one, have suggested that the lithosphere in the cratons might be even thinner, about 100 kilometers. How do we reconcile this? So first, I want to show you something which I find rather cool. I couldn't resist to show you. This is how can you define the cratons from seismology in an objective way without invoking any geological information. So these are two models. These maps are extracted from two recent tomographic models, one a Harvard model, one of our latest model from Berkeley. And what is done here is you take the model, and at each point on a grid of 2 degrees by 2 degrees on the surface, you extract the shear velocity profile at that point. And then, so you have a family of profiles as a function of depth for the upper mantle, and then you classify them into clusters. So clustering analysis is a mathematical way of classifying objects into families of like properties. And so here, I won't go into the details, but essentially you have to specify the number of clusters that you want, and then you get your profiles put into that into two families if you specify 2, 3 families if you specify 3. Here, what is done is specifying 6 families of profiles I don't have time to go through the details of why 6, maybe I will a little later, but you can see that if you specify 6 families of clusters and you look at what the distribution of the different families are, which is here indicated by the colors, what pops out is 3 regions in the oceans, the red, orange, and brown, and then 3 regions mostly in the continents, but very clearly the green region here is a region that pops out with very, very fast velocities here as a function of depth. And one can argue whether, the depth where all of these curves meet is 200 or 300 kilometers. There's a poster by Beth Paulson yesterday that was analyzing tomographic models in this fashion. But essentially what I want to just point out is that these cratons do pop out as the fastest by quite significantly. So this is another view of these clustering, where for each region you see the mean, so colored by the region, and the cratons are here with the mean, and this is, the black curves here are 50 randomly selected profiles across cratons, which give you an idea of the range of velocities. And these colored curves are just the averages for the other 5 regions, showing you that this is quite a significant difference. And I think I would disagree with what Beth was showing on her poster, because the next region here is the stable regions of continents, and they are quite distinct from the cratons, actually, in this analysis. So yes, so the way we do it is you start with 2 regions, you get oceans and continents, you add the 3rd region, you divide the oceans in 2, and the same, you add 1 region, and you get the stable versus tectonic continents. 5 regions adds another region in the oceans, and 6 regions is what I showed you there. So this comes entirely from just looking at the velocity models without any preconceived ideas. Okay, so now, the continents are fast, as seen by these. These are mostly constrained by these surface waves and overtone data, so long period waveforms. What if we want to say, well, can we explain these maps by just thermal structure? And here is an attempt to do this, where the seismic waveforms were inverted directly for temperature. So what it involves is having converting shear velocity, having a relation between shear velocity and temperature, which you get from mineral physics with some, of course, uncertainties. But the most important thing is that you also have this effect of dispersion in the velocities due to attenuation, because the Earth is not completely elastic. So attenuation depends on temperature in a nonlinear fashion. And once you include attenuation, you get these nonlinear effects of temperature. And if you see these maps, they look very much like what the normal velocity maps that you get from tomography, except that look at the temperature scale here. It's very asymmetric. That is, there is much more here negative temperature corresponding to these continental cratonic regions, and there are hot temperatures. And this comes out of this nonlinear effect through the effect of attenuation. And so this asymmetry actually is very, from this what comes out is that you really can't explain this only by temperature. So this is an example in the Canadian Shield, where we compare the geotherms obtained from xenolith with this temperature profile obtained from interpreting the seismic data only in terms of temperature. And this is the average in this region in the circle, and then this is the range. And you can see that the temperatures that you get from tomography are much too cold. So this is one argument that has been made by many other authors for a compositional signature in the cratonic lithosphere.
Are the xenoliths, can you establish that the equilibration is occurring just prior to?
Don't ask me. I don't know. Any geochemist wants to comment on this?
Well, this could be a frozen profile from some time in the past.
Yes. Well, you know that I don't know. This is simply taken from the literature and taken at face value. What exactly it represents, I'm not sure.
Represent the quench temperatures of the xenoliths when they erupted on the surface. And I think Jericho is on the order of 50 million years old.
Uh-huh.
So the geotherm is 50 million years old.
Oh, I see. Okay. So it doesn't necessarily reflect ancient.
No, I mean
but it's the current. Right.
Were established age. And Jericho, I'll show it tomorrow, gives ages up to 3.5 billion years. But this profile is the temperature profile in the mantle, that area, when these were erupted 50 million years.
Okay, so that they don't necessarily represent current day geotherm.
Because magnesium iron exchange at these kind of temperatures, 1,000 degrees. Yeah, I mean they're in equilibrium up to the point where they're about the surface.
Okay. Okay, so let's get back to these velocity profiles. Again, the cratonic regions here. So here, these are just samples for two models, so you get a range of, you know, the uncertainties in all of this. But the cratonic regions here are in the continuous line. The black line is the average, global average in these two models. And you can see that the differences persist to about 200, 250 kilometers. You can pick your choice, but I like to pick it where this negative gradient here, somewhere between, say, 200 and 260 kilometers. So these, everything that I've said so far is based on these long period waves. I just want to remind you that these long period waves have depth sensitivity. This is the depth sensitivity for the fundamental mode, first higher, second higher mode, etc. But ooh, what happened there? Huh. Okay. I hope it doesn't do it again. So anyway, the point I want to make here is these are there's good depth sensitivity, but still no sensitivity to the details. If you want to have sensitivity to possible discontinuities, you have to invoke other techniques. And one technique which is widely used is the receiver function technique. So yesterday, Dave Stegman walked away from a poster saying, I don't understand receiver functions. Let's see if I can make you understand it today. So, essentially, right. So now these are teleseismic waves. They come from the source here onto the station region. Here we're looking at the very top. The illustration is for MOHO and maybe a mid-crustal discontinuity, but this would still be valid for deeper discontinuities. They arrive here as P waves, and at the MOHO you can have the P wave just be refracted and go all the way to the receiver as a P wave. But you could also have a conversion, right, as Ed taught us last week, where the P wave is converted to an S wave and then arrives as an S wave at the receiver. The converted phase will be called PDS, meaning, oh, actually, I think the S is a little s, is that right? But anyway, it's meaning that it has interacted with this discontinuity. And you can see that you can also have a P wave that will be converted as an S wave at a different, shallower discontinuity. The P waves travel faster than the S waves, so this direct phase, the main phase, will arrive first. And these conversions will arrive later. So you can devise methodologies that will deconvolve the energy related to this main P phase, and from there you can basically extract these conversions, and that's essentially what's done.
Yes. If using that last diagram,
Yes.
How do you know that's not the inverse, that is what's happening at the source as opposed to the receiver?
So you're saying reverse this, and I could have here the source, and I have a P wave converted to an S wave. You would know because of the travel times. Because if it was on the source side, the P part would be short, so you would have a much longer time delay between the S and the P, right? I guess. Yes?
Why are they called receiver functions?
I have no idea. Does anybody know why they're called receiver functions? It's kind of an ugly term.
When you say receiver, you mean the region of the
Region of the station, receiver.
broad region.
Well, yes, because depending on where they're coming from, right, they could, this one is coming from this azimuth, so the actual conversion points are not right under the station, right, and could be coming from here. So you have to take all of this into account. Yes?
In response to Bill's question, you can have reciprocity for one earthquake in one station. You could just make your triangle a star.
Yeah.
And look at all the P waves when they get to the station. But what doesn't work is you have earthquakes at all different depths. And everything's coming up to one station, so when people do these analyses...
But the travel time works, right? My argument works, doesn't it? Is that if you're looking at teleseismic, the P wave is faster than the S wave. So if you have a long path which is P compared to a long path which is S, you're going to have a very large time difference. So it's not.
If you made your triangle your earthquake,
yeah.
You start your journey as an S wave and convert it to a P wave right into the source. So the wave.
Oh, I see. In that sense, yes. Okay. Yes, that's a different kind. And thanks for pointing it out because. Yes, there are other ways of telling.
That's true. Yeah.
Yes. So in response.
Robert, can you repeat why these are called receiver functions?
Because you basically end up with analyzing effects that are near the receiver. Right.
That's for all our audience. I think the function came from like transverse function, and I think you could do this.
Anyway, let's not spend time on it. It's really not critical. Okay, so there are, of course, so one thing that Ed mentioned is, here I give you the example where the incoming wave is a P wave, and then the conversion is an S wave, and this is called a PDS. But you also you can imagine that the S wave is coming after the P wave, so it's coming in the coda of the P wave. But you could also have an S wave, starting an S wave and convert to a P wave, and these would be called SDP. And in that case, the conversion arrives before the main phase. And it actually has other advantages, but that's one kind of advantage. It also has disadvantage. No, it's not complete. No, it's partial. So that's a good point. Those phases are faint because they're only partial. Yeah, here you would have a P wave which would go somewhere else, right?
And there would be some energy that's lost.
Yes, and you might even have some conversion, some reflection, although, yes, depending on the distance.
But the advantage, one thing here is that because the S wave is mostly on the horizontal and the P wave is mostly on the vertical, that allows you to bring out the
Yes, good point. I didn't mention that, but that's important. So you have complications because it would be simple if you only had the direct phase and the converted phase. But there's a whole suite of phases that are secondary phases that are generated at the same time, which you're not really interested in. I mean, they help you determine the Moho thickness, the Moho depth, but you're not. If you're really looking for example, this doesn't give you really if you're looking for a discontinuity deeper here, the converted phase from the, oh, actually, this is sort of the receiver function thing. So this is the P2S at the MOHO. And you're looking for something deeper, a discontinuity deeper, a mantle conversion. Here it's marked in this particular case here. But you can see that these other phases that are interacting in the crust come here. In this particular case, they come later, so you can separate them. They're stronger. These reflections are stronger than the conversions. But depending on the depth, because this time here, this is delay time, depends on the depth of your discontinuity, where the conversion has occurred. And this could be happening right in the middle of these, right? So this makes it quite difficult to sometimes. And if you use S to P conversions, there are fewer problems related to this because of how these travel time differences work out. And I'm thinking specifically about discontinuities at lithospheric depths. Okay. Yes?
Can you rule out the reverberations, though, if you can see a relationship between with move out?
Yes, yes, you can see it here. But it's not always, the move out is not necessarily that great. I don't know if maybe Huayu can comment on this. He's a specialist, receiver function. Okay, so now that you understand a little better, I don't know. Wait a minute, yes?
So you actually get these zones of total internal reflection at the top here. It's looking like you're getting multiple bounces
Yes,
off
yes,
the top of
yes,
the boundary.
yes. So these are strong.
So these are the earthquake communication layers. They just kind of go like whales in the thermal layer of the ocean.
The reflection from the bottom is not total, but the reflection
From the top is total. Yes, right. Good point. Yes. Mm-hmm. Right. Yeah.
Can you say a few sentences about topography on the boundary and its effect when you're averaging inversion?
Yes. Yes, it will defocus things, right? It will defocus things if you have topography, but on the other hand, you can, if you have azimuthal coverage, you can, you can actually distinguish. If you have dipping layers, there are other considerations like anisotropy, which will make things a little more complicated. But yes, there are complications. But the principle, do you understand it now, Dave? A little bit?
Yeah,
better. Okay, good. So based on this type of study, Reichert and Shear published this paper in Science a couple of years ago where they detected, okay, so there's also one thing I didn't mention is that you can detect velocity increases or velocity decreases with depths, and they will look differently on your receiver function. Essentially, they will show up as on one side or the other side of your diagram here. Sorry. Here you have these going this way or going down, right? And that will tell you whether it's a velocity increase or a velocity decrease. So they detected this velocity decrease as you go from the surface of the Earth, so a low velocity layer at these depths globally. And this is a cool study. The only problem I have with it is that in the title they say depths of the lithosphere asthenosphere boundary. If you look at this, what's special about it? What's special about it is that this discontinuity is nowhere, even in the cratons, deeper than about 120 kilometers, right? So if this is the lithosphere asthenosphere boundary, so what are the surface waves telling us? They're telling us it's deeper, it's at least 200 kilometers. So, how do we reconcile this? And basically, it will become clearer, this is most likely not the lithosphere asthenosphere boundary. Okay, so the next kind of tool that I'm going to be introducing is seismic anisotropy. So I'm going to have a few slides, a little bit of background, try to make it simple. I hope it happen. It's simple enough. But anyway, in an isotropic structure, basically seismic waves propagate with different velocities in different directions. We saw yesterday, Quentin was talking about anisotropy in different properties of minerals, but also in elastic velocities. And the main causes of anisotropy, as Ed already mentioned in his first class, were shape-preferred orientation or lattice-preferred orientation. In particular, in the presence of flow, the interesting property, anisotropic crystals will tend to align in a particular direction. I didn't put here in the direction of flow because it's a slightly more complicated, but roughly speaking, it is in the direction of flow if you apply after enough strain, causing seismic anisotropy at a macroscopic level. So you can have an anisotropy at the microscopic level, lattice-preferred orientation, and then at the macros, it could be very strong for single crystals. At the macroscopic level, all the crystals will not be aligned, but you could still end up on average with detectable anisotropy. Primarily, anisotropy is found in the upper mantle because the upper mantle has a large component of olivine, which is very anisotropic. In the lowermost mantle and in the inner core, I'm not going to discuss.
What about lichens in the crust?
Oh yes, the crust also. I'm sorry, the crust for me almost doesn't exist. I'm sorry, but of course, the crust is very anisotropic. Yes, when I say upper mantle, I include the crust. Okay, so just 2 slides with equations, but when we study wave propagation in an elastic medium, one of the main relations is the linear relationship between strain and stress, or Hooke's law, I guess, which most generally, because we're working in 3 dimensions, relates the stress tensor, 3x3, to the 3x3 strain tensor through a 4x4 tensor, a 4th order tensor, which is the elastic tensor. And here, okay, the strains are related to the displacements. UI are displacement. And this notation means that this is the derivative of the component in the direction I with respect to the component of your space reference frame in the J's direction. Okay. So anyway, this is the important relation, and one has to realize that in the most general case, this elastic tensor has 21 independent elements. Okay. So if we really wanted to describe structure in the Earth, relate seismic observations to structure, we should be worrying about 21 independent elements and their spatial variations and depth variations. Of course, the special case which we all like is the isotropic medium, where you have only 2 of these parameters called the Lamé parameters, which can be expressed in terms of the shear and compressional modulus or in terms of the VP and VS velocities. Okay, so again, this is very, very rough and basic, but in a general anisotropy, you have 21 independent elements. There are symmetries. The 4th order tensor has 81 elements, and because of symmetries, you end up with only 21. Surface waves, and including overtones, are sensitive only to a subset of these, to 1st order 13 of these 21, and only a small number can be resolved, as I will be showing. So typically, you will describe this anisotropy in terms of 2 components: radial anisotropy, which is the vertical transverse isotropy that Ed was referring to, which is described fully by 5 parameters, and then an azimuthal anisotropy, which are the other 8 parameters. So, very briefly, so the radial anisotropy or transverse isotropy, these terms are used equivalently for the upper mantle, can be produced by shape-preferred orientation, so layering, for example. It can also be a component of flow-induced anisotropy, so lattice-preferred orientation. So these are these 5 parameters, and they can be expressed in in terms of the velocities, that you basically have two velocities depending on whether the wave is polarized horizontally or polarized vertically. And so these are these two parameters here for shear waves, these two parameters here for P waves, for compressional waves, and then a parameter describing behavior in intermediate directions. So on the other hand, there is azimuthal anisotropy has been observed in oceans. So azimuthal anisotropy means that the direction depends on the azimuth of the propagation with respect to a reference direction, which is usually north. And this was first observed by Hess in 1964, where in mid-ocean ridges you have these velocities that vary depending on the direction with respect to the spreading direction, maximum being in the spreading direction of the plate. Okay. So for azimuthal anisotropy, and particularly long periods, the velocity depends on the direction of propagation in the horizontal plane and can be described to first order by terms in 2 psi and 4 psi, where psi is the azimuth generally counted counterclockwise. Clockwise or counterclockwise? Clockwise from north, I think. Anyway, and these A, B, C, D are combinations of these 13 elements of elastic tensor that the surface waves are sensitive to. So the 5 from transverse isotropy, and then there are 6 corresponding to the 2 psi terms here, and then 2 corresponding to the 4 psi terms. And in general, this is still too much. So you want to simplify. What Montagner and Nataf proposed in the late 1980s is the concept of vectorial tomography, is that we can assume in the upper mantle that the medium is orthotropic. It has a hexagonal symmetry with inclined symmetry axis. It's a simplification, but to first order maybe a manageable one. And in that case, you can replace all these 13 elements by only 5, where essentially you have a radial anisotropic medium, but not around a vertical axis, around an axis which is inclined. And so the axis can be defined by 2 angles, its dip and its azimuth, theta and psi. And so you end up with only 7 parameters to describe. And in practice, that's still too much. Surface waves are primarily sensitive to the shear component. So we simplify it even more by assuming that the only thing that matters are the ln, psi, and theta. Actually, I should have left this f term here because it may be important. But anyway, you can bring it down from 7 to 5 by assuming some proportionality or some relationship between the shear and the compressional properties. For the upper mantle, using laboratory measurements of mantle rocks, you can establish such proportionalities and use them. This is, again, approximation and somewhat controversial. But in practice, when we discuss surface wave measurements of anisotropy, we really only start with this. And most people don't even, in fact, only Montagner and Nataf really produced a model that tried to get constraints on these angles, but typically you would only describe the radial anisotropy in terms of these 2 quantities, plus some description of azimuthal anisotropy. Yes, yes. So there's 2 simplifications. First, the orthotropic medium, and then also these, how do you relate the P anisotropy to the S anisotropy? Because it also varies. It varies with composition, so it varies with depths, and so there are. But these are the common simplifications that are made. So why is anisotropy really interesting to resolve? First of all, you can't make a model, a surface wave based model, without including radial anisotropy. There's the so-called love to Rayleigh wave discrepancy, that you cannot find an isotropic model that will fit. In general, you can't find an isotropic model that will fit dispersion curves of both Rayleigh and love waves. If you introduce radial anisotropy, you can do it. And this is why, for example, the PREM model, if you're familiar with it, if you've worked with it, actually has the first 200 kilometers are radially anisotropic, because on average on the Earth, you really need that radial anisotropy to describe the observations of dispersion of surface waves. So anyway, so this was just an aside. So if you have information on three quantities, very simple kind of cartoon here, a convection cell, right? Simple 2D convection cell oriented in some way with respect to north. From the isotropic velocity, you expect the velocities to be slow where the material is rising and fast where the material is sinking, right? So that gives you already some idea where, on some aspects of the geometry of these cells. The radial anisotropy, which will give you, is described, since we boiled it down to two parameters, L and N, you can describe it either as L and N or the isotropic velocity and the ratio of the VSH to VSV squared, actually, the Xi parameter. This Xi parameter is going to be greater than, it would be 1 for isotropic. It is greater than 1 if you have horizontal flow, and it is less than 1 if you have vertical flow, again, in this very simple cartoon. So that will tell you also, give you also some constraints on the geometry, where are the flows dominantly horizontal, where are the flows dominantly vertical. And then if you have information on azimuthal anisotropy, you can orient this cell in space, how is it oriented with respect to north. Right? So these are good things to strive for when looking at constraints from seismic long period waves. If you look at models, tomographic models again, this is in the upper mantle at 140 kilometers. This is already somewhat dated, but models from the early 2000s. What you can see is that they agree pretty well on their large-scale features, but if you look at the Pacific, for example, this model has much more blue than this model, right? And in fact, this can be explained very simply by the effects of anisotropy. This model, S20RTS, is constrained by Rayleigh waves in the top 200 kilometers, whereas this model, the Berkeley model, was constrained only by love waves. It was a SH model. Okay, so this difference is not simply because one model is wrong and the other one is right. It really reflects the presence of this, actually lateral variations in this radial anisotropy. And these two models here use three components, and so they're constrained both by, they're sort of hybrid in the sense that they're constrained by both. And so this particular structure is, has been discussed in many papers. The sort of, in particular, it was pointed out very strongly in this paper by Ekstrom and Dvorensky in Nature 1997 that there was something special about the Pacific plate. Now the color scale here is, this would be SH faster than SV, and this would be SV faster than SH. So you have this SH faster than SV centered in the Central Pacific that's very strong. Montagner also had a paper on this, but there's also something similar in the Indian plate, actually. So what about the continents, since I'm supposed to be talking about the continents? So again, in the continents and in the cratons, you see, depending on which polarization of waves you're looking at, you see differences in the depth extent of the fast velocities. So here you have, this is an anisotropic model, which has an SH component and SV component. And you can see that the SH component, the roots of the, if you call these roots, extend well below 200 kilometers, up to maybe 300 here in these different cross sections across different shields, whereas the SV essentially by 220 kilometers or 200, yeah, I mean 200, 220 exactly is difficult to pin down, but you have lost this. So this effect is due to anisotropy. And so this led us at that time to propose, a cartoon, because you also, in tectonic regions and in oceans, you also have this kind of observations. So this anisotropy that you see would be actually under the lithosphere, and that might be one definition of the lithosphere-asthenosphere boundary would be the boundary below which you see this SH faster than SV that would indicate this horizontal current motion. So keep this in mind. At that time, this was sort of a sketchy cartoon. So just turning to azimuthal anisotropy, there are more recent work. There's a new paper by Ekström in 2011 that was recently published I think in JGR, which is an update. But what is shown here is these little red lines indicate the direction of the fast axis of azimuthal anisotropy, which direction is the fastest, and the length of it is proportional to the strength, how anisotropic is it. And you can see, and on the background is the corresponding isotropic model. So you can see the specific rise here, and the alignment at, this is a 60-second period, which is mostly sensitive to depths of 80 to 100 kilometers. In the oceans, you can see this alignment at least near the ridges corresponding well with the plate motion direction. Note that in the continents, we have a different direction here at this period. So in fact, another way of looking at anisotropy in the upper mantle is this shear wave splitting. I'm going to explain what shear wave splitting is in a minute, but just to point out that if you have a model of a surface wave derived azimuthal anisotropic model, you can predict the shear wave splitting, and specifically the SKS splitting that this model, from this model. You can predict it, and you can plot the fast axis of predictions in SKS splitting all over the world. And then you can compare it to actual measurements. And whereas, there's not that many measurements in the oceans, there's more measurements now, but in the continents, there has been this puzzle that, in fact, the predictions from these surface wave models disagree with the observations. For example, in North America, you have this fast direction from SKS splitting, which is sort of north-east, southwest, and it's somewhat different from the predictions of this. So there has been this puzzle. So let me discuss very briefly the shear wave splitting. So this is actually, I think, a cartoon from Ed, right? It's after Crampin, but I should cite also Ed art. So if you have a wave, a shear wave, entering an anisotropic medium, it will split into a slow wave and a fast wave. I guess Ed already explained that. And so as the two waves travel through this anisotropic medium, they will get separated more and more. And when you pick them up at the surface of the Earth, or if they then go whether or not they go through some isotropic medium in the meantime, you will be able to distinguish these two waves and compute and basically measure the travel time difference, which will tell you something about the anisotropic medium. In fact, it will tell you something. There are trade-offs between the time spent in the anisotropic medium and the strength of the anisotropy. Right? So now SKS is an ideal wave, or is a really convenient wave to use for measuring splitting due to anisotropy. Other waves are also used, but SKS has the particularity is that it goes as a P wave in the core. So as it comes out of the core, it is polarized as SV. Right? We discussed this. Ed discussed this previously. So if the medium is isotropic in the mantle, it should be visible only on the radial component, but there should be no energy on the transverse component, right? And that so that if you see transverse component energy, it must have originated somewhere along this path here in the mantle. Okay? And now if you have measurements over many different directions, you can also say that your observations, if you take an average over a station, say, will reflect the upper mantle, because you may have picked up some anisotropy in D double prime, but if you average over many directions, you're likely to have diminished that contribution with respect to what you get from the upper mantle. So this is an example of observations where you have here the radial, let's concentrate on the horizontal component, the radial and transverse. You see the SKS here, and then the SKKS, which has one bounce point coming in somewhere here. And you can see there's very strong energy on the transverse component, and this is diagnostic of the presence of anisotropy. And so, people design methodologies to estimate this anisotropy that is being picked up, and essentially what you measure is a travel time difference between the fast and the slow, and you basically have a polarization plot. So how strong is the radial component with respect to the transverse component at any point in time in this waveform? And if you have an anisotropy, you will see an elliptical kind of plot of the polarization plot here, and you can remove it by correcting for anisotropy, again by a method such as method of transverse function. What kind of an isotropic structure do I need to get rid of this effect and bring it back to a linear particle motion plot? So if all Earth if your wave travels along the great circle path, you will have only radial sort of motion. You won't have transverse motion at all. But sometimes you may have a wave coming from a different angle than the great circle path. But if you correct for anisotropy, it will still be a flat thing. And so the two parameters here are the time shift between fast and slow waves and the direction of the fast velocity axis. Okay. And if you have many data from different azimuths, you would typically plot this kind of time lag versus the azimuth corresponding to the fast axis, and you will get an optimal, value, couple of these two parameters, which will give you your solution. And whereas if you have only one azimuth, you may have a lot of dispersion, first of all because these waves can pick up anisotropy from different parts of the mantle, and also because it can be shown that depending on the actual layered structure of anisotropy, the details of the variations with back azimuths will vary, in particular as a function of the order of the layers, layered anisotropy. But if you look on average, and I don't think I have time to go into details on this, you will get a robust station average with just one number for time and one number for angle, which will represent essentially the integrated effect of anisotropy on these under this station in the whole upper mantle. Okay, so now if we combine isotropic inversion, so we've already taken out the radial anisotropy from here, and azimuthal anisotropy on a continent, and I'm going to give the example of North America, for which we now have a large amount of data owing to the EarthScope program. This is sort of a rough long wavelength study, but showing that the isotropic S velocity shows large lateral variations. There's no scale here, but this is plus or minus 4% or something like that. You can see very clearly the Rocky Mountain front here, the boundary between the craton and the western tectonic regions in this map. But by the depth of 300 kilometers, most of the heterogeneous structure has disappeared. I mean, you still have some signature, and if you were looking at a smaller scale, you might see some details, meaningful details. But at this scale, everything has disappeared. So basically, in everywhere you are below the lithosphere. If you look at the azimuthal anisotropy, on the other hand, at the same two depths, you see quite different fast axis directions. In the craton, here in the cratonic blue region, it's more or less north-south, and in the Western Pacific, it's more or less northeast-southwest. The red arrows show the absolute plate motion in the hotspot reference frame, and so in the Western Pacific here at 100 kilometers, where you're already below the lithosphere, you can see this agreement with the absolute plate motion. Then when you go down to 300 kilometers, everywhere you have alignment with the absolute plate motion. So this, going back to this cartoon, it seems that what we're seeing is, again, that you have anisotropy below the lithosphere that is not only radial anisotropy, but also azimuthal anisotropy in the direction of current plate motion. So, yes?
Are you going to go into detail about the Western U.S.? I mean, there's a lot more complexity.
Oh, yes. No, I'm not going to talk about the Western U.S. at all. I'm going to talk in more detail about the craton. Sorry. Because...
It's just that, I mean, given Dave's talk before yours, I mean,
yeah, there are, of course. I mean, I could.
Patterns that are consistent with motion around the spectrum flat.
Yes, yes, but that wasn't what I was going to talk about. Sorry, but there is, and we could talk about it more separately. So yes, so I'm just focusing on right now on the lithosphere-asthenosphere boundary, and particularly on what goes on below the lithosphere, where it seems like these results, again at very broad scale. I'm not going into any details here. There are many more details that you can see in more regional studies, and even in the global studies, as you'll see, in the large-scale studies, the large continental-scale studies. But what this indicates is that there is some kind of flow below the lithosphere. We don't know from these data; they're not sensitive enough what kind of flow we might have. There may be even other kinds of models. So with the advent of EarthScope, it's recently been possible to go into more details in the craton, and this is work actually by Huayu Yuan, who's sitting in the back here. The reference is missing because I removed a number of slides on this topic for the sake of time. But what we're going to we're looking now is at more details, again, still large scale, but across a certain number of profiles across the craton. So AA prime is here northwest to southeast at the top. BB prime is more or less east-west. And then CC prime is a sort of a crooked path which follows the locations where there have been some sampling of xenocrysts. And what is shown here in these depth cross sections is the color scale represents the azimuthal anisotropy, the deviation from the absolute plate motion of the North American plate. So the direction of the fast axis with respect to this absolute plate motion. And if you do this, you can see that essentially you delineate three regions in the upper mantle. Two that are likely, that we would like to interpret as being in the lithosphere, and then everything below the lithosphere is quasi-parallel to the absolute plate motion. But in the lithosphere, what's interesting is that you find that there is to this level of resolution, you have two domains. One domain which is pretty much orthogonal to the direction of plate motion on average, and another domain at the top which is probably coincidentally, although not necessarily, in the direction more in line with the absolute plate motion. This direction turns out to be also the direction of sutures in the crust in this region. So this is a more likely explanation. But you can see that this boundary between these two domains varies strongly with depth. It starts very deep here, very thick at in the middle of this, in the craton here, and then as you go to younger provinces, it thins out, and we lose it. We don't have much resolution at depths shallower than 50 kilometers, so this has been kind of blanked out. This same thing is seen on this cross section, and the different tectonic provinces have been shown here. And what is interesting is that this kind of layering, or these domains, seem to agree quite well with the information that is obtained from the geochemistry in terms of depletion. So this Mg number is the percent of forsterite, and the very high numbers indicate depletion, which you can see two levels here along these crooked lines, which seem to bracket this boundary very roughly. So this is an indication that perhaps this domain here is the domain of depleted lithosphere, as sort of evidence both by geochemistry and seismic anisotropy. The important thing is that this boundary now here, this lithosphere-asthenosphere boundary, is mapped much more precisely by this change in the direction of anisotropy than you could do with just the tomography, the isotropic velocity, and radial anisotropy tomography. Basically, this boundary is defined to less than 20 kilometers precision.
What is the relative amplitude of anisotropy in different areas there?
Okay, so I'm going to show you a slide later which shows the average kind of with respect to depth, so that will give you some idea. But it's less strong than in the western US, where the anisotropy is much, it's really well developed at 100 kilometers. I'll show you that. Actually, actually this one shows something. So this is just an example of two stations within those cross sections where here is the VS profile with depths, with this negative gradient that defines the lithosphere-asthenosphere boundary, but in a very kind of not very well resolved way. And this is the anisotropy strength, azimuthal anisotropy strength, which goes through two minima. So it's very strong in the shallow part, and then it goes through a minimum with a slight maximum in between, and then it becomes large again below the lithosphere. So this is quite well defined by the strength, which goes through a minimum, which is understandable because you're changing direction, so you're going through a minimum. And this is the direction. This is the absolute plate motion direction, and this is the blue is the direction of the fast axis. It changes, flips here away from the APM and then comes back to the APM. In this particular region, it starts like here, changes, etc. The red line is just the gradient in this quantity, which just to emphasize the changes in direction. So it turns out that very simple modeling, borrowing the computations that were done by Cooper et al., that allow simple relationship between the thickness of the chemically distinct lithosphere with the sort of blanket that you might have around it and below it, you obtain this kind of simple relationship. If we now assume that this is the boundary of the chemically depleted lithosphere, and we want to estimate what would be the total thickness of the lithosphere, assuming the rest of it is thermal, you end up with, so the white curves, these are gradients in the azimuthal anisotropy, which is why it looks all these colors, but they emphasize the region where the direction changes, here in red in the mid-lithosphere, and here the lithosphere-asthenosphere boundary. So when you start with this boundary and estimate how thick the lithosphere would be, you end up with these broken red line, which actually coincides quite well with the measured LAB position from the seismology. And on top of this, you plotted the results from receiver functions, where you see this negative jump, right, to a low velocity, some low velocity zone here, which coincides quite well. Not so much here, but you have to keep in mind this is a region of strong gradients, so it might not. I'll show some better figures. So you see where I'm getting at. I'm getting at saying that what the receiver functions pick up is not the lithosphere-asthenosphere boundary. It's something that is in the middle of the lithosphere, which may well be related to what we see from azimuthal anisotropy in the way we're doing it. So.
So does that argue against a sharp interface?
Yes. So that argues that this interface is sharp, but the lithosphere-asthenosphere boundary is actually not that sharp. Which is under the craton, right? So the receiver functions don't pick it up. And if it is a thermal kind of dominated, boundary, then that's what you would expect. It would be spread over a large depth, and so you could see it with the surface waves. And the azimuth anisotropy actually provides a better way of defining it. So again, so this is a cross-section across North America of receiver functions, where you see, so in blue would be the detection of converted waves corresponding to the MOHO, which is an increase of velocity with depth, and then the red would correspond to a decrease of velocity with depth. You see that there are some large variations, but on average, they pick up something in this depth range of about, in here it ranges from 60 to maybe 100 and something kilometers. And if you plot on top of this the velocity structure from tomography, you can see that this depth range is well in the middle of the fast zones of as picked up by velocity tomography. On the other hand, in the western US, the lithosphere is much thinner, and in fact, what the receiver functions are picking up most likely is actually the lithosphere-asthenosphere boundary, which is much sharper, as is shown in many studies. So this somehow reconciles these different discrepancies on how what is the thickness of the lithosphere in the craton. The receiver functions are picking up mid-lithospheric boundary, and the tomography is seeing more of the whole depth range of the structure. And then the azimuthal anisotropy picks up something also in this depth range. The question as to whether this is the same thing as what is picked up by the receiver functions or not is an open question, actually. What it requires is looking at whether you can pick up some anisotropic signal from receiver functions, and whether you can match that with what you find from surface waves. One more thing I wanted to show is this. So there seems to be, at least in North America, but actually there is evidence for the presence of mid-lithospheric boundaries in other cratons. I have an example coming up, but in other cratons and many other more detailed studies in North America have detected it as well. But I wanted to just point out this complementary type of data, the long-range seismic profiles, which, so basically this is offset. This is from your source, your artificial source, and how far you are from the source, and you're aligning your seismogram and picking up the energy arrivals. This is for two different regions of a cratonic region, and it's in some region of the world. I can't remember where exactly this particular one was taken from, but it's some craton, and this is more a sort of younger type region where the velocities are slower, right? So the first arrivals will come later. But if you concentrate on this one, you can see that there is a break here, which this community, the community of the long-range seismic profiles people, have found already a long time. I mean, they've been talking about it for many years. They call it the 8-degree discontinuity. 8-degree because it happens at about 800 kilometers on average, and this would correspond to a depth range of about 100 kilometers. So again, what you see this offset is that the first arrival here arrives along this line, and then all of a sudden it's delayed, meaning that you are going into some low velocity zone. Right? And this cartoon I don't particularly like, but if you look at the blue curve, it's showing that this part of this diagram corresponds to waves traveling here, and then you go into a lower velocity zone here, and then back. And they have these authors have described this zone as being a zone of strong scattering. It's not, well, it's not really visible on this diagram, but if you look at the actual records, you see behind those first arriving waves, you see a lot of secondary waves showing that this region here is complex. We don't quite know exactly what it is, but it's complex. So this basically led us to revise this simple cartoon. We still have this LAB that is now well defined from the azimuthal anisotropy, but not from the receiver functions. And within the lithosphere, this is totally probably wrong. But anyway, the important thing is that you have basically two domains, two first order in the cratonic lithosphere, and this chemically distinct layer, and a sort of a thermal blanket. And if you look at just the velocity structure, now you flip this should be the western US and this the craton. The western US velocities are slow, down to 200, down to about 150 kilometers. The purple here are the cratonic velocities. These are averages. There's a global average and there's a continental average here. And then if you look at the azimuthal anisotropy, so this is the strength of azimuthal anisotropy. In the western US, it's very strong, right under the lithosphere. In the central, in the craton, you have two domains, one in the lithosphere and this bump in the asthenosphere, which is weaker than the one you have in the western US. You're much deeper, and the properties of materials are likely, I mean, we know they're different at these depths. So, and again, bringing back the geochemistry, the composition, this may well correspond to this depleted part of the lithosphere. So I like to think about it, and so this brings back this model where essentially the craton would be about 200 to 250 kilometers thick in terms of where you define the boundary between the convective and conductive geotherm, and would have this chemical part of it, which I like to think as maybe being the ancient, the really ancient lithosphere. But being a seismologist, that's all I can say. I can really not say much more. Yes? Sorry, I didn't hear. Why would you have in the less depleted route an anisotropy that is in a different direction than the current plate? Good question. It reflects some past process that maybe, I mean, if you think in terms of formation of the lithosphere by subduction, it would be compatible with east-west trending subduction, and the sort of trench parallel kind of fast axis anisotropy would be compatible, but there are many other possibilities. What's not compatible is the idea that a plume, formed the base of the lithosphere under North America, because you would expect radial, anisotropy that would go in different directions, sort of from points, whereas you see it more aligned. So.
Barbara, actually, plumes create circular
Mm-hmm.
So they don't flow out, they flow in a circle.
Right, but we don't see that either. Yeah, at least at this scale. At this scale. So again, I'm almost done. Does this hold on other cratons? And I should have more examples, but this is one example of work by Levin and Park in the Arabian Shield, where pretty much, this is from converted phases, which also, basically makes the case for a discontinuity in the mid-lithosphere, which is often referred to as the Hales discontinuity. And it's in this study they point to evidence that this is an anisotropic discontinuity. Okay, so I guess that's all I have. Just bringing back that, in order to continue studying these questions from seismology, you really need to combine different types of data. This is the same message as previously, that any of these data alone cannot really solve the problem. SKS splitting gives you an basically average over the upper mantle. You can have some more detailed, kind of make 2-layer or 3-layer models, but there are issues with that if you do it only with SKS splitting. Receiver functions give you information on discontinuities, and then long period seismic waves gives you information on the large scale structure. So that's it, I guess. Yes?
On the 2 slides before, on the North American cartoonish section, where would you put the moho again?
Here? This one? Oh, the moho depth would be somewhere here. Right? It's about... The seismological moho would be what? Between around 40 kilometers in North American Craton? Right? I don't know. Gabby knows that better. Yes. Rick.
This works well for North America for all the reasons you said, but also the one you didn't say is that we know that at least in the slave, the upper part's 3GA or so, 3.5 GA, and the lower part has a lot of 2GA material.
So yes,
there's a sequence of development of this craton. Mm-hmm. But if you go to Africa, you see old ages all the way to the bottom. The local receiver function work shows very little in the way of energy in the lithosphere down to 200-something kilometers. So it's only this record at Shear result that shows anything at 100 kilometers. So I don't know what that
well, I'm aware of a study of azimuthal anisotropy that is sort of in the works, and that actually does show also some variation with depth. So I don't.
Well, but we have Zenos from there that don't.
That don't have any.
They show the same age, the same composition down to 220 kilometers.
Okay. But in Australia, on the other hand, you also see.
Australia is another story.
Yeah. Okay. So.
So the Crustal are smaller rings. That means it doesn't actually sample the same natural material.
Well, maybe you want to.
Come from the surface down to as low as the volcano sample. And in the slave, go back to the Griffin paper. So there's an example. So the stuff in the yellow are the typical things that are expected in cratons. These are things that have had a lot of melt and movement in them. And it ends at about 150 kilometers shown here. And what you see underneath it are a lot of both ferritites that are more fertile, meaning they have a larger metal component available in the porcupine ferrocene, basically. But you also see a lot of melts in that region. And there's also this age difference where the top layer is 3 billion and the bottom layer is more like 2 billion. So these are really a layered lithosphere that was created in multiple events. So the zeniths are tracking, or you get zeniths, they're tracking the whole history of the lithosphere. That answer?
Okay, yes, Zach.
When you're starting to do the full waveform tomography, can you incorporate the splitting?
Yeah, well, that's what we're doing. Actually, I didn't mention it. Thanks for pointing it out. everything I showed you on azimuthal anisotropy over the continent and these layered structure has been obtained by combining the long period waveforms and the SKS splitting. Basically, if you only, that brings back to this controversy about if you have only surface wave, like fundamental mode surface wave models, and you predict SKS splitting, it doesn't show you something that's compatible with the SKS splitting. That's because you lose resolution at depth. So if you have both the waveforms and the SKS splitting, which pinpoints the kind of integral effect, you actually can, you get more depth resolution this way.
What about the conversion near the surface? So are those, like if you're making a model that you were saying about finite element models on Saturday, can those models tell you the magnitude of the conversion at these discontinuities?
Oh, you mean like from the receiver functions? Yeah. Yes, they can. They tell you, they can give you some constraints on the velocity drop or the velocity increase, right? And depending on the strength of the conversion, you can, and also the sharpness, of course, because you need a sharp discontinuity to have them in the first place. Yes.
In one of the slides, you show the result of program memory.
Of what?
It shows the upper cross, lower cross, and fundamental. But I'm wondering whether in the upper cross case, whether the anisotropy is still consistent with wave motion or some grading.
No. So in the upper layer, the direction of fast axis seems to be, more or less parallel to the current absolute plate motion, but that doesn't really make sense. I mean, unless you think in terms of Wilson cycles and something like that. But it's more the relationship is more with the current Suter zones. I think I have a slide to show this.
Arabia.
Oh, about Arabia? You were talking about Arabia? Well, let me show you this, though. I mean, we've worked on North America, but anyway, so here you see the suture zones are the red and black lines, very roughly speaking, and the blue are the direction of fast axis at 50 kilometers, so really in the top layer, and they align with these. But now Arabia, yes, so this was. So you were wondering about what exactly? Sorry.
Oh, because in the upper cross, there are some structures like a ball of Shearing. I don't know whether that also has
Yes, of course. In fact, anisotropy is pretty strong in the crust. So.
In the upper crust.
Upper crust, yes.
When you incorporate the SKS splitting to your results, do you incorporate just the average?
Yes, so that's very important. No, because the average, you can relate the average, the station average, to the integral in depth of the various layers, and that average is not dependent on the ordering of layers. It's a robust measurement, and so it really pinpoints your how much anisotropy you have over the entire upper mantle, and then the surface waves give you the more of the depth dependence with a better resolution at the top. So then we've shown that if you do an inversion with only surface waves, you find the same directions of anisotropy. You find the same model, except the strength in the bottom layer is much reduced. But you have to use the average. If you use just measurements at at particular azimuths, then it gets much more complicated. To combine the two types.
Should predict an azimuthal pattern that you could check.
Yes.
Actually matched.
Yeah, but you do, right? Because then from your model, you can predict the shear wave the SKS splitting. We do that, and it matches pretty well. Much better if you have this zone of strong anisotropy below the lithosphere than if you don't. Gabby.
Yeah, I'd just like to add to the complexity of this kind of
receiver
function LNB and what the surface waves actually see in the cratons. We see that for the old oceanic
thing there is that both as we go across the swell and we map the thinning, for whatever reason, of thinning of the lithosphere and tomography, the receiver functions actually also map a shallowing of that discontinuity that's within the lithosphere. So we might actually, for the oceanic lithosphere, also have to find a model that has
Yeah, that has two layers. Yes, that's right. Yes, yes, definitely. It should be easier because surface waves have more sensitivity at shallower depths, right? So you don't really need, you may not even need the SKS splitting. I mean, you have it in some parts, right? But if you think about the ocean basins, we don't have any data for splitting data because there are no stations.
Well, and there's also a depth depends on anisotropy also. And for some weird reason, the shear wave splitting actually only picks up the shallow part and not what's going on in the Asthenosphere. I have a puzzle anyway.
Okay.